Let's study effectively with Miss ICT Skill Builder.
In this video, we break down how computers represent different data types, text, images, and sound, using the basic unit of binary, bits, and bytes.
Every time you send a text, stream a video, or scroll through a meme, you are experiencing a highly calculated illusion. Behind the glass, your device is processing a relentless, invisible stream of binary ones and zeros. The central processing unit, the brain of your computer, is governed by microscopic electrical switches that are either on or off. It has no innate concept of human language or alphabets unless we provide a precise mathematical translation blueprint. That blueprint is called a character set. It acts as a strict lookup table, assigning a specific binary sequence to every individual letter, number, and symbol we want to display on screen. This table is part of the standard ASCII code, the original character set developed for early computers. Relying on an 8-bit system, it is limited to 256 characters. This covers standard English keyboards, mapping letters and basic punctuation to numeric values. But as computing spread across the globe, a system capped at 256 slots hit a mathematical wall. The global internet required a massive expansion to support every written language on Earth simultaneously. Looking at this grid of Unicode characters, we see the result of that expansion. Unicode upgraded the basic blueprint to 16-bit and 32-bit sequences, providing tens of thousands of character slots to accommodate non-Western alphabets, complex scripts, and emojis. Without this evolution in character sets, global digital communication would fail. Computers would remain isolated calculators, unable to parse or share the languages of the people using them. This logic extends directly to visuals. Screens display images through a massive grid of tiny, discrete dots called pixels. As we see in this black and white matrix forming a face, the most basic image relies on a 1-bit system. Every pixel is given a binary value of exactly 1 or 0, dictating whether it is solid black or solid white. To introduce shades and hues, we use a concept called color depth. By assigning longer strings of binary bits to each individual pixel, we increase the data payload for every dot on the screen. Pushing that color depth to 16 bits or 24 bits allows a single pixel to represent millions of distinct color combinations. But adding all those extra bits to millions of pixels creates a mathematically heavy file, requiring significantly more storage space. To reconstruct this grid, the computer also requires metadata. These are secondary instructions stored within the file that tell the device the precise dimensions and resolution of the image it needs to build. The visual realism we see in modern media is achieved by feeding the processor heavier mathematical values. Every increase in visual fidelity is traded for an exponentially larger file size. Audio presents an entirely different challenge. Real-world sound travels through the air as a continuous, unbroken analog wave. A computer, which operates in discrete digital steps, cannot naturally store something that never pauses. To capture sound, we pass it through an analog to digital converter, a mechanism that chops that flowing wave into a series of digestible digital slices. This graph illustrates sound sampling. The blue sound wave is intersected by vertical lines representing specific time intervals. At each interval, the computer computes a discrete numerical snapshot of the wave's amplitude, or loudness. The frequency of these snapshots is called the sample rate, measured in hertz. A low sample rate leaves large gaps between data points, resulting in jagged audio, while a high sample rate maps a smoother curve. We also measure sample resolution, or bit depth. This dictates how many bits are used to record each snapshot. A higher resolution gives the computer a much more precise vertical scale to plot the exact loudness of that specific moment. Engineers face a constant balancing act. Combining a high sample rate with a high sample resolution yields pristine audio, but it forces the computer to write a massive amount of data every second. Clear digital music is an illusion created by taking snapshots of a sound wave so rapidly that the human ear cannot detect the gaps, always demanding a heavy storage toll. Whether it's text, pixels, or a voice recording, digitizing reality always demands a trade-off. Increasing the precision and global reach of our data will always cost storage space. Let's see how well you process that concept. Here are 3 quick questions to test your attention. Question 1. If the ASCII character set handles the English alphabet, why was the invention of Unicode mandatory for the modern web? The answer: to break past the 256-character limit. Unicode provided the mathematical space required for global languages, non-Western alphabets, and symbols. Question 2. Look at these side-by-side images of a caterpillar. If you double an image's resolution and its color depth, what is the exact consequence on the file size? The file size increases significantly. You are multiplying a higher total number of pixels by a heavier binary value per pixel, requiring more data for the same image. Question 3. How does a recording sound if it is captured with a severely low sample rate? It sounds distorted and choppy. The computer missed too much audio data in the gaps between those infrequent snapshots. The entire digital universe is a rapid binary translation. Once you see the math behind the screen, you understand how the illusion is built.
Thanks for watching. If this helped you clear up the concept, hit that like button and share it with a friend who might be struggling with it too. Let's build those skills together.